Everyone. Today I'll discuss the foundations of crystallography as it pertains to energy storage materials. So, in order to understand certain key factors that govern properties that we care about, such as lithium-ion diffusion in lithium-ion battery materials, we need to discuss how we're going to classify crystal structures of the materials that we're interested in. So the topics in crystallography that we're going to review and practice today include translation, crystal systems, Bravais lattices, symmetry elements, screw axes, glide planes, space groups, crystal planes, and directions. And we're going to build up the terminology in crystallography to ultimately ask the question, to answer the question, how is crystallography used to predict battery performance? Okay. So we start off first with translation. So you see here that if we have a generic example, such as the letter A, in one dimension, we can see that we can translate this A in space by a translation distance of T1. We can expand that and make a lattice of the letter A by translating in along this direction as well as along the T2 direction. And these directions have to be non-collinear. We can then extend the situation so that we translate in 3 dimensions. So here, imagine that these A's are above this set of black A's. So it's above the page, right? And when we step away from this generic example of the letter A and replace, these positions with atoms represented by black dots and blue dots here, we can then form different unit cells with lattice parameters such as A, B, C, and angles between the lattice vectors alpha, beta, gamma. So the materials of interest that I listed here are all cathode materials, and they have crystal structures that are listed here, such as R bar 3M for lithium cobalt oxide, FD bar 3M for lithium manganese oxide, and lithium iron phosphate, which is orthorhombic, listed here as PBNM. So how do we go from this part of the slide where we understand the crystal structure and then to the battery material performance? So in class we talked about the structure of graphite and how it's hexagonal, but how do we get there? How do we build up so that we can say that graphite has a crystal structure of P63 over MMC? Well, we need to start a classification system where we can categorize the material in 7 different crystal systems, or one of 14 Bravais lattices, 32 crystal classes, and then with symmetry elements such as screw axes and glide planes, we can form 230 space groups, right? All starting from here. So to start off with, if we were just to put the atoms at the corners of the unit cell, then we can have 7 crystal systems: triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, cubic. So this is in order of increasing symmetry. And we can describe the constraints of the lattice parameters and angles like so. So here we can say, well, if A is equal to B, and C would be different by presumption since it's not listed here, then that would satisfy the constraints of a tetragonal crystal system. For orthorhombic, A would have to be different from B and C. And then triclinic, A, B, C are also different. And for the angle constraints, alpha, for tetragonal, alpha has to be equal to beta is equal to gamma, and all these angles have to be 90 degrees. trigonal, gamma is 120, similarly for hexagonal, and then for cubic. Now, sometimes you'll see the crystal systems, trigonal and hexagonal, listed together as a crystal family, it being in the same crystal family. Now, that's different than a crystal system. Here, they're delineated as two distinct crystal systems. So how do we then build up to 14 Bravais lattices? Well, if we just had atoms at the corner, then we have the primitive lattices that you see here. Here are the 7. And we can denote these different crystal systems with more specificity, the Bravais lattices, with these Pearson notations. There's also Hermann-Magen notation, and so one can look up, how to go back and forth between these notation systems. I'll stick with the HM system for this particular course. Now, if we were to put atoms at the base of the unit cell, then that would be base-centered, and the notation there is C. For face-centered unit cells, here we have additional atoms at the bases for the orthorhombic crystal system as well as the cubic crystal system. And then for body-centered, now we have the atom in the body center, and the notation is I. So now we're building up. We have 14 Bravais lattices, and if we add symmetry elements, we can then have additional crystal classes. So there are 32 crystal classes. So what are these elements of symmetry? Well, they are rotation, mirror, and also inversion. And so if you see the Hermann-Magen notation as 2, 3, 4, 6, that's indicative of the n-fold rotation. So here's 2-fold, 3-fold, 4-fold, 6-fold. And how many degrees do you rotate that by? Well, you take 360 divided by the n-fold. So 360 divided by 2 is 180 degrees. So in this example, for a 2-fold rotation, for this particular molecule, you'll, if you rotate this fluoride to here, you see that, that's symmetric by this rotation axis. Now, here's the notation, the Schoenflies notation, that's more common in chemistry. Once again, these are equivalent. Now, if we have a mirror plane in our molecule or in our periodic arrangement of atoms, then we denote that as M. In Schoenflies, that's sigma. And then we can also invert. So we have one element here, and then that's rotated. Then we can also denote rotated and inverted through the center of symmetry, so that here we see the plane. So we can denote here, this is bar 4, rotation, rotoinversion symmetry. Now, there's 3 bar, there's bar 4. Bar 2 is just the mirror, so we use the more specialized M notation for that. Bar 1 is denoted as I. So in this example, we have this is a rectangular prism. So can we find these symmetry elements within this shape? Well, there are 3 unique rotation axes. So we denote that as Cartesian coordinates. We see that there are, if you rotate 180 degrees, around this axis, and this axis, then you get back the original shape. So that's, so we denote that as 2, 2, 2. There are also 3 mirror planes. So we'll write that as 2m, 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 but also coincidentally, the mirror planes are perpendicular to the rotation axis. So then we actually write it as 2 over m, 2 over m, 2 over m, and we read it as 2 over m. So with these symmetry elements, there are symbols within the international tables for crystallography to guide you to say, okay, if let's say you have twofold rotation symmetry, so if you start off here, you rotate 180 degrees, you would end up right there, and that is the symbol for twofold rotation. And one can look up all of these symbols, but I've also listed them here for 15 out of the 32 crystal classes. So here you see triclinic, monoclinic, orthorhombic, tetragonal. And when you see Laue notation, that means there's central symmetry or inversion. And then for the remaining 17 symmetry elements, the other crystal classes, you see that there are 5 in trigonal, 7 hexagonal, and 5 in cubic. Now, if we put this all together, we can see that in terms of the point groups, for each crystal system, we can denote all the point group symmetries as well as the essential symmetry. So what is the minimum symmetry that each crystal system must have to qualify for each crystal class? And so for triclinic, there isn't any. It can just be one, right? But there has to be twofold rotation or mirror for the crystal structure to be considered at least monoclinic, and so on and so forth. So you can see here there are some minimum, all the minimum values listed here. Okay. And the International Table of Crystallography is readily available because Ohio State has already paid for the license. See here, you can see access. So if you go to library.osu.edu and type in International Tables for Crystallography, it's all available in Volume A, Space Group Symmetry, in the 2006 edition. 2016 is not available yet. But here you can click through the 230 space groups and you can go through that. So this concludes part 1 of the crystallography